Hey everyone, it's me. Welcome back to another episode of Physiology 2, especially for you. In this video, the topic is circulation. As you can see here, it entails the heart and the entire cardiovascular system. So let's have a look at what we can learn. First of all, again, I want to advise you to know your numbers. As a good physio, it's very important to know your numbers. So measure your own resting heart rate, look at your friends' values, and try to measure as much as possible so you can always have a nice comparison between what you would expect to be normal and maybe sometimes something that is a little bit abnormal. In this table, what you can see are some average values. You see an average male and an average female person, and basically the difference in cardiac output is proportional to the difference in body size. So what you would expect at rest is that the cardiac output for an average male is about 5 liters per minute, whereas for females it's 4 liters per minute. And what you can see in this table is that it is accompanied by a resting heart rate that is approximately the same. But because, again, of the body size difference, you would expect stroke volume to be slightly higher for males compared to females. If you take the product of heart rate and stroke volume, you get cardiac output. In this video, we will focus a lot more on heart rate, stroke volume, and cardiac output, so no worries if you didn't follow completely. We will go through all these variables step by step. The FIG method was developed a long time ago to actually measure cardiac output through the measurements of VO2 and the measurement of the AVO2 difference. So what you can see in this picture is that if you're able to measure the oxygen consumption in the muscles through oxygen measurements and CO2 measurements inside through the ventilation, and you would measure the mixed venous blood O2 content and you would compare it to the arterial content, you can have a look at the difference, the AVO2 difference. And then here in this formula, you can see that this is a way to calculate the cardiac output. If you know VO2 and AVO2 difference, cardiac output can be calculated. The underlying formula of this method is stated right here. The Fick equation is one of the most important equations in exercise physiology. So what you see right here is that VO2 can be calculated by taking heart rate, multiply it by stroke volume, and multiply that by the AVO2 difference. As you should know by now, heart rate times stroke volume is cardiac output. So this is a simplified version of that same formula where you can state that VO2 equals cardiac output times AVO2 difference. And what you saw in the previous picture is that I basically flipped this formula around. So if you mathematically change this formula, you will see that you can measure cardiac output, or you can calculate cardiac output by measuring VO2 and dividing it by the measured AVO2 difference. And in a lot of the exercise physiological literature, we will work with measurements and values that are derived from this formula. So stroke volume is the amount of blood that is being pumped out of the heart every beat. And what is important to realize is that the heart will fill during the diastolic phase, and then it will be emptied after the systolic phase. It will just not be completely emptied, so that's what you can see here with these variables. The end systolic volume is the amount of blood that is left after the systole, so after the contraction. That's never zero, there's always a certain amount of blood left. The end diastolic volume is the amount of blood that's in the heart after complete filling, so after the diastolic phase, hence the name, end diastolic volume. For an average person, as you saw on the table, stroke volume is around 70 milliliters per beat at rest. And here you can see that it's calculated by having a 135 milliliter of end diastolic volume and the amount remaining after the systole and systolic volume 65. That will give you 70 milliliters of blood pumped out every beat. Well, heart rate frequency, quite straightforward, the amount of beats per minute. For an average person, you could say Any value between 50 or 80 is what you could expect. But if you look at exercise physiological research that included professional or elite biathletes, for example, heart rate values can get as low as 30 beats per minute. And for some people, untrained or just for genetic reasons, could be up to 90 beats per minute. So it's a huge range, and it all depends on stroke volume and some other factors. So again, cardiac output is the product of heart rate and stroke volume. So to regulate heart rate, we can have a look at, to regulate cardiac output, we can have a look at stroke volume and how that is regulated, and heart rate and how that is regulated. Stroke volume is regulated in three different ways, or at least there's three factors involved that can determine stroke volume. The first one is preload. The second one is contractility, and the third one is afterload. And especially the first two, the most important ones, we will focus on in this video. Preload is actually the connection to the Frank Starling mechanism. So a long time ago, we had two scientists, Mr. Frank and Mr. Starling, that realized that there must be also in cardiac muscle cells a sort of a length-tension relationship, similarly to what they had seen in skeletal muscle cells. And what the Frank Starling mechanism basically says is that if you fill the heart more, it will automatically also pump out more. So more filling means more stroke volume. And in this chart, you can see graphically how that is done. On the y-axis, the vertical axis, you can see stroke volume. And on the horizontal x-axis, you can see end diastolic volume. So again, the normal value that I showed you earlier in the table, roughly 135 milliliters, for example, of end diastolic volume would give you this 70 milliliters of stroke volume. So those are normal resting values. Now, what happens in case of an increased venous return? So there's more blood flowing back to the heart, there's more filling of the ventricle, and that automatically then will bring the stroke volume also up to a higher level. So the cardiac muscle cells basically get stretched, and as they get stretched, they will shorten more, and that will bring more stroke volume. So it's all related to venous return. And the venous return is to a great extent determined by, for example, the muscle pump and some other physiological features. But the muscle pump allows the veins to actually push the blood back up because of the valves, for example, in your legs that are available and prevent blood flow in the wrong directions. So, for example, back to your toes is prevented by these valves. So if you have a little bit of a contraction of your quadriceps or gastrocnemius, for example, it will push up the blood in the veins, and that will help in the venous return. So this is one of the practical implications where the muscle pump can really be beneficial. And for example, why you could advise someone to do a cool down in order to keep the muscle pump working to stimulate venous return and then also increase stroke volume as a consequence. The second factor is contractility. And what should be clear is that contractility is not the same as the Frank Starling mechanism. So contractility is basically saying, an increased contractility is basically saying that at any given end diastolic volume, you could have a higher stroke volume. Whereas the Frank Starling mechanism says that if you have an increased filling, there will be an increased stroke volume. So contractility together with Frank Starling mechanism can bring up stroke volume even further. So in this graph, you can see again the green line that you saw before, where you see the normal Frank Starling mechanism applied, that if end diastolic volume would increase, stroke volume would increase. But here you can see that the orange line shows the situation where due to sympathetic stimulation, contractility is increased. And then you can see that at the same end diastolic volume, in this case 135 again, you can see that the normal resting stroke volume will then change from this to this. So to quantify the amount of contractility, in literature, very often you see the ejection fraction. So the ejection fraction is simply the ratio between stroke volume and end diastolic volume. And with these normal values that I showed you earlier, the ejection fraction of a normal person at rest is roughly 50%. So only 50% of the amount of blood that's in the ventricles after filling and the diastolic volume is pushed out as stroke volume. And with exercise or with just other reasons for sympathetic input to go up, contractility can be increased. In some pathological situations, you see that the ejection fraction can only reach a certain value, and that's why the ejection fraction in some pathological definitions is included to specify the severity of a cardiac condition. So increased sympathetic input will increase contractility, and that will then also be accompanied with an increase of the rate of contraction, but more importantly, the contractility is about the force production of each cardiac muscle cell. So what you see in this chart is for a particular cardiac muscle cell, the normal rate of force development over time. So here you see force development during contraction, here you see time. So a normal cardiac cell would contract and generate force according to this line, whereas with increased sympathetic stimulation, you will see that the peak occurs earlier, so the frequency goes up of the next one if that would be with the same input, but also the maximum force that's being produced by this cardiac muscle cell is higher than for this one. So this really shows an increased contractility due to sympathetic stimulation. But how is this possible? Because if you look at skeletal muscle cells, then hopefully you remember that there was this all or nothing principle. So for skeletal muscle cells, they were either active and generating force at 100% or 0. Well, let's have a look at some of the differences to see if we can explain this. To control the amount of force output for an entire skeletal muscle, what you could do is increase the number of motor units that are active. Within one motor unit, again, it's all or nothing. So that's where you cannot regulate overall force output. But in skeletal muscle cells, you can recruit more motor units in order to recruit more fibers, and that would be accompanied by more force overall. The summation of twitches happens in skeletal muscle cells. So we always have this tetanic contraction that will push up the force output of a single cell more than after a single twitch. But in cardiac muscle cells, both mechanisms are not possible because the number of fibers that are active in the cardiac muscle is always 100%. Because you want this contraction, remember from the last video, to always start from the bottom up, so from the apex upwards, so the signal will actually spread from cell to cell, and the idea is that every single cardiac muscle cell is active in that particular sequence. So through the gap junctions, remember, the electrical signal could be transferred from one cell to the other. So it's not possible to recruit more cardiac muscle cells because they are all active already. And also the summation of twitches is not a way to increase force output. And that's simply because you don't want a tetanic contraction, because that would mean that the cardiac muscle cell would be contracted constantly, and that would not allow the relaxation and the filling of the heart, so that would completely eliminate the pumping function of the heart. So both mechanisms that are present in skeletal muscle cells are not present or possible in cardiac muscle cells. So what's left? Basically, it's about calcium. Calcium is required for the formation of cross bridges in a similar way to the function of calcium in skeletal muscle cells. So the amount of calcium is actually regulated, for example, by the sympathetic input. So a normal level of calcium that is being released will allow a certain number of cross bridges to be formed, but there's always a certain amount of cross bridges that are not formed because there's not sufficient calcium in a resting situation. So with an increased sympathetic input, more calcium will be released than at rest. More calcium means more cross bridges means more force. So by regulating calcium levels, the heart can regulate overall contractility. The third factor is afterload, and afterload is basically having a consequence on stroke volume, and it's maybe not something you can actually regulate instantly as you could with the preload and contractility factor. But afterload basically says that if you have a higher pressure in the arteries, for example, a higher blood pressure that leads to a higher pressure in the aorta, it will take more effort of the cardiac muscle cells to overcome the pressure in order to open up the semilunar valves. And if the heart or the cardiac muscle cells need to produce more force, according to that same force velocity relationship that we saw earlier for skeletal muscle cells, you can see that they can shorten less. And if they can shorten less, stroke volume will be reduced. So someone with a higher blood pressure will have a lower stroke volume due to this third factor. So then you can combine all of these factors in this chart. So here you can see the beginning and here you can see the end. Here you can see cardiac output, again determined by stroke volume multiplied by heart rate. And here you can see the different routes of regulating heart rate through the sympathetic input or through the parasympathetic input and through the sympathetic input. Here you see that epinephrine can influence frequency and contractility, and here you can see also the input of the sympathetic system on the contractility of the heart to upgrade stroke volume, and here you can see how the Frank-Starling mechanism can also upgrade stroke volume. So this chart summarizes the different factors that we discussed until now. Well, how does it work if you look at training effects? So we know from literature that stroke volume is something that can be improved due to training. And the mechanisms are basically related to the three different factors that we mentioned earlier. The blood volume can go up after, let's say, 12 weeks of aerobic training, which will increase the diastolic filling, will increase the preload, Frank-Starling mechanism is triggered, and stroke volume is higher compared to pre-training. Also, contractility will be increased because you can have a higher input, more sympathetic input, and greater systolic emptying, so less residual blood after a full contraction. And finally, also, although maybe minor compared to the first two factors, the reduction in blood pressure that could be accompanied by an increase in blood volume and a reduction in viscosity could reduce the afterload, and that also could lead, as we just saw, to an increase in stroke volume. Well, if you look at some athlete values compared to sedentary, regular people, you see that the resting heart rate compared to, for example, this average of 70 can be expected to be lower because of an increase in stroke volume. So if someone at rest has a higher stroke volume, at rest you need roughly the same cardiac output, you can live therefore with a lower resting heart rate. So very often we measure heart rate because it's a lot more practical than measuring stroke volume, but we do that to actually reflect the stroke volume values indirectly. So here you can see in this table a comparison between untrained and trained values, where you see here that heart rate multiplied by stroke volume will give you again that same cardiac output as before. And here you can see that for a trained male person, you would expect the resting heart rate to be lower because of a higher stroke volume, but still at rest the same cardiac output. In this table, you can see the comparison between rest and max values. So here you see that compared to the resting heart rate, the maximum heart rate could be around 190, for example, and then stroke volume can shoot up to 150, for instance. So if you take the product of heart rate and stroke volume, you can see you can easily reach cardiac output values of roughly 30 liters per minute, which is 6 times more than the resting cardiac output of 5. So please have a good look at your own values. Take a heart rate monitor. Just use the manual method to measure your resting heart rate. Try to measure heart rate at different exercise intensities so that you can have a good idea of what your values are for different intensities. So finally, we make the transition to the blood. So here you see the different components of the whole circulation. And here in this table, although in the video probably a little bit too small, you can see how many milliliters of blood you can expect in the different parts of the whole circulation. And here you can see, or at least I can tell you, that in the veins you would expect the most amount of blood in a normal situation, especially at rest. So to repeat what the functions of the blood are, as you know from previous videos, of course, to transport O2 and CO2 and other waste products, but also the blood is very important to buffer temperature, especially the water is very important in buffering temperature so that homeostasis for temperature and for other reasons can be maintained. And that also relates to the buffer, as we saw before in a previous video. The bicarbonate buffer, for instance, is part of the blood, and one of the reasons why it's doable for the body to keep the pH levels within a very small range, all thanks to the composition of your blood. So the blood is composed of 45% roughly formed elements, 55% water, and that determines the hematocrit value that normally you would expect to be around 45%. And this hematocrit value is something that definitely in professional athletes sometimes is monitored, because artificial enhancement of the hematocrit value is often not allowed. First of all, because of health reasons. If you have an increased viscosity, it could be more risky because of an increased pressure, but also because of the possible increased performance, because if you have more red blood cells, potentially you can deliver more oxygen to the system, so potentially your VO2 max could be increased, and that's something that at least doping agencies will always try to monitor. So again, knowing what normal values are will allow you to also check when something is abnormal. Yeah, so what I mentioned before, the resistance to the flow is very important. So the viscosity is something that's related to the resistance. And this is one of the reasons why the hematocrit value is actually reduced after, let's say, 12 weeks of solid aerobic training, because a lower resistance will make easier blood flow. So a normal training effect is actually a slight reduction in the percentage of the hematocrit value, whereas the total blood volume will actually increase. Well, during exercise, you can also lose some of your blood volume, at least temporarily, and that could be due to the whole process of filtration and absorption. That net will lead to some interstitial fluid that will be increased due to some movement of water out of the bloodstream into the interstitial fluid space. But also due to sweating, for example, you can temporarily lose blood volume, which could lead to an impaired performance if the blood volume loss is significant. All right, that was it for this video. I hope you liked it. Thank you very much for watching, and I really hope to see you in the next video.